gasification.
Thank you, Hugh. It's interesting because I retired from Grand Rapids Community College about 1.5 years ago. So I look at that as my later part of my career, not my early part. So we're talking about my retirement as being my current part. I don't quite vision it that way yet. So today I'm going to talk a little bit about wood gasification. And I know that there's been a lot of interest in this lately. People seem to be somewhat confused about what it is and what it isn't. I've studied wood gasification for quite a long time, renewable energy in particular. I was the renewable energy manager at Grand Rapids Community College. And I'm sort of a hands-on, do-it-yourself sort of person. And I'm going to show you that this is probably not for everybody, but it might be. So let's take a look at what wood gasification is all about. This presentation is my investigation into this, and I've done a lot of research into wood gasification, most of that in the European arena. America has not done much with wood gasification. There are no really good scientific, technical articles on wood gasification in the US. The National Renewable Energy Lab probably has the best information out. But if you want to research this, I would say look at Norway, Sweden, Denmark, Germany. Europeans have done this for quite some time and really have the technical information about it. My intent here is to give everybody some information about what this is, what it isn't, clarify some of the terminology related to it, and how this can be looked at as a renewable energy source. If you want to do this, you better be prepared to do a lot of tinkering, build a lot of stuff. This is not something that I think the average person can get directly involved with. If you want renewable energy that you can just put there and it just does its thing and gives you the feedback, I would say go solar. Don't do this. All right, so to talk about this, I'm going to have to talk a little bit about chemistry, and I'm going to have to throw some numbers out here and a little bit of physics, and I'm trying to keep it to a minimum. I've expressed everything here in both Celsius and Fahrenheit, and you'll see that they're differentiated by everything in Fahrenheit is in red numbers, and everything in Celsius is in black numbers. Most of this presentation is going to cover wood gasification in general. And then I'm going to describe a project that I'm intending to implement at my farm this year and hopefully have this system operational by Christmas. That's a goal. And next year, if I do this presentation, I'll have some real, actual data to support what I'm going to show you here today. So, I want to take a little survey. We're not going to introduce ourselves with this number of people. Takes way too long. How many people in here partially heat with wood? Okay. How many people in here wholly heat with wood? Oh, there's a couple. All right. Not as many as I thought. How many people in here process their own wood? You don't buy it. You actually cut it, haul it, stack it, and all that. Okay, good. How many people in here have ever gasified a piece of wood? Oh. Well, I got news for you. You all have. And I'm going to show you how that happened. Whoop, these are hooked together. Okay, so we've all used matches. It doesn't matter really whether you've used a wooden match or a paper match. The principle is the same here. And if it was a little darker in here, and you could look at this, you would see that that flame is not actually quite touching that piece of wood. It is slightly off of that piece of wood. Okay, and we have always left over this little black piece when we get done. So what happened there when we struck this match? So for a long time, people didn't have matches. It was quite a lengthy invention, actually. It took 100 years to come up with the chemical compound for the tip of that match that allows, when you make that strike on that box, enough friction to produce enough heat to ignite the phosphorus that's on the head of that match. And that phosphorus then ignites what's called potassium chlorate, heats it up, and it releases oxygen. Because we're just shy of the temperature at which wood ignites, which is 451 degrees, and I'm sure we all remember the book Fahrenheit 451. Okay, that's where that came from. That's the temperature at which wood will spontaneously ignite. So we strike this tip of this match, we produce enough heat to get this wood to burn with oxygen. But that is not enough actually to sustain this burning. What is happening then is that the heat produced from the striking of that match heats this wood up enough that the gas that's contained in that wood is being released into that flame. The flame on that match as it was burning here is roughly in this range, 600 to 800 degrees centigrade, or 1100 to about 1500 degrees Fahrenheit. That wood will release gas starting at about 200 degrees centigrade all the way up to about 2000 degrees centigrade. So once we start the process, the heat from the flame is forcing the gas in this wood to be released into the flame. I'll cover that in a little bit more detail. Another example of that that's kind of interesting, you may have seen this. This is a common candle. Anybody know what the wick of that candle is made out of? Cotton. Okay. Gasification can occur with any biomass. Doesn't have to be wood. Wood happens to be one of the better ones. But cotton will work also. So we have paraffin wax surrounding that wick. The flame is burning. Is that flame burning the cotton? Or is that flame burning the paraffin? You sure? Okay. Let me get it. It ain't coming up high enough. No. Let's try it again. I think there's too much breeze in here. Okay. So I reignited that candle without touching that wick. Okay, how'd that happen? The gas, same gas that was coming off that piece of wood is coming out of that piece of cotton in that wick when I extinguish that flame. And that gas is flammable enough. I've gotten it, if you get in a real still condition, I can get about 2 inches away and reignite these candles like that. Okay, so we have gas coming here from both the paraffin and from the wick. So what's left over? So we took that piece of wood, we ignited it, we baked it, we got it hot enough to release gas, and what's left over is this black char. Now depending on what you use that char for, it's got a couple of different names. If you're going to then burn the char, which is flammable, it's called charcoal. And we've all used charcoal briquettes. If you're going to use it in the ground as a soil amendment, that's called biochar. They are exactly the same thing. But you hear the word biochar now being used a lot. But it is charcoal. So the chemical process here is called pyrolysis. And it is a thermochemical process, meaning it is a chemical process that is driven by heat. And we are decomposing that piece of wood rather quickly at an elevated temperature, and the best way to do it is without oxygen. Now obviously that match is drawing oxygen from around the room. The flame is actually keeping the oxygen away from the wood. So we have a heat source, we have a fuel source, piece of wood. We'd like to put that fuel source inside of a box, an oven. And we'd like to heat it up and bake it. And as it gets hotter and hotter and hotter, that piece of wood starts transforming. And when it transforms, it releases several substances. It releases some substances that are liquids. We call those tars. It releases some substances that are gases. Those are the ones we're interested in right now. And then it also has a byproduct of biochar, most of the time, not all the time. We'll cover that in a minute. Excuse me. So here's where it gets a little technical, but I'm going to refer back to this particular slide a lot, so we need to spend a little time on it. So at about 200 degrees centigrade, or 392 degrees Fahrenheit, pyrolysis starts happening. This piece of wood that we're baking starts transforming. And in that temperature range, it remains still basically a solid, 75% of it. And it starts producing tars. Liquids start coming out of it. And these are the names we give those tars when we're in this particular temperature range. It also starts releasing gas, but not very much of it. So we turn up the heat a little bit, and we start baking it at a higher temperature. The next phase is called slow pyrolysis, 300 to 400 degrees centigrade roughly. And at that temperature range, we start producing a lot of charcoal, 35%. And we start transforming it less into a solid piece of wood and more into tars and gases. So this phase here, it's pretty equally split. And these are the names of the gases we give here, or the liquids, I'm sorry, that we give it here. We probably recognize one of these. Larry? You know, what's one you just talked to me about yesterday? Creosote. Okay, so cresol is the precursor to creosote, the basic chemical substance of creosote. So depending on what you want to achieve in your pyrolysis process, you work at different temperature ranges. So let's go up one more. We'll go up a little bit higher. We're getting pretty hot now, 400 to 600 degrees centigrade. And we start producing a lot of bio oil, a lot of creosote, a lot of tar. What temperature are most of your wood stoves burning at? Yeah, 400 centigrade?
No, I don't know.
No. No, but most people are running their wood stoves in this range right here. And then when you run your wood stove at that range, it distills a lot of tar out of the wood. That tar collects on the inside of your stove, the inside of your chimney, as creosote. But it's composed of more than just creosote, but these are the tars that are contained in there. So the chemical industry pyrolyzes wood at different temperatures depending on what they want to get out of it. If they want to extract oil out of wood, they use these temperature ranges. If they want to extract biochar or gas, they use different ranges. We're concerned with, we want to gasify this piece of wood and use the gas, but at the same time, we'd like to probably minimize the amount of tar and the amount of charcoal that is left over. And we'll hit on that in a minute. So let's go up one more step. So we keep turning the heat up on this piece of wood, and we get up in the 600 to 800 degrees centigrade range. And at this range, we start producing what are called secondary tars. A secondary tar is a tar that you cannot detect. If I gave you a piece of wood and you did a chemical analysis on it, you would not find those tars in it. Those tars are created out of these tars going through a chemical transformation due to the heat. But we start producing a lot of gas, 75%. So that piece of wood now is being converted to a gas. And we'll look at that gas in a second. So let's keep cranking it up here. We crank it up a little bit more. Anybody know what the word tertiary means? Third. Okay, so we're producing now another level of tars that were not in that piece of wood. You could not detect them. The heat is creating them out of the existing tars. These are the guys down here called tertiary tars. And you may have heard this phrase, and we're going to cover it at the end, called PAH. Anybody know what that means? Okay. We'll hit it at the end. But these are the bad guys. These are the guys that everybody doesn't want to create because of the amount of cancer-causing agents that are in them. So there's kind of a sweet spot in this whole process of taking a piece of wood and pyrolyzing it into a gas. And in my opinion, that sweet spot is right here. Because what we'd like to do is create the most amount of gas, the least amount of tars, and the least amount, or some amount of charcoal, biochar, and not have an excessive amount of ash created in the process. So I'm going to refer back to this, try and keep these in mind though, the temperature ranges that we're talking about here and what's going to be achieved at each temperature range. So let's look first at, I'm going to focus on this spot right here. The rest of this presentation will be on, if we gasify at this temperature, what do we get out of this?
When you say tar, what do you mean by that?
Okay, it's, well, let's go to, I'll show you in a second. Let's look at the gas first and then we'll look at the tar. So wood gas, that's one of the names for the gas. Oh, let's back up one sec. So there's a bunch of different names. If you read all these studies, everybody doesn't use the same terminology. That's a big problem with this whole field, is that the terminology is not used consistently. So when they say we're going to make a gas out of this wood, some people call it pyrolysis gas, wood gas, syngas, or producer gas. They are essentially all the same thing. So what does wood gas look like at that temperature range? This is what it's composed of. We talk about hydrogen cars and the hydrogen economy and hydrogen renewable energy. Wood gas has a lot of hydrogen in it. Carbon monoxide is a flammable gas. Methane, same thing, you produce in natural gas, biodigesters, another major constituent. Some other gases that aren't real prevalent but are very powerful is ethylene, acetylene. Where do we use acetylene at? Welding, right? Yeah.
Is that the same for different tree species?
Same for what?
The chemical properties that you get from burning different tree species like wood?
Different tree species will produce different percentages of this. This is based on a hardwood, a dried hardwood. Okay. And it's another whole science, what wood you put into your gasifier and what kind of gases you get out of it. And then there's also ethane in here. So those 5 gases combined are what cause the combustion in wood gas. There's also some non-combustible gases that come out. Carbon dioxide, about 18%, and nitrogen, about 6%. This came from NREL, their studies on wood gasification. And remember, this is at this particular temperature range. If you gasify at the other ranges, the same gases come out, but the proportions are changed. Okay. Okay, so what is tar? Tar is the liquid that comes out. And remember, we're doing these different temperature ranges, starting down here at 200 degrees centigrade, and we're going to stop here at about 600 degrees centigrade. So if I take a piece of wood and I cook it at about 200 degrees centigrade, the tar I get out of it is basically lighter than oil, or excuse me, lighter than water. It's an oil. It's lighter than water. And the main one that we're all familiar with, there's a bunch of them, is turpentine. So that's how the chemical industry gets turpentine out of a piece of wood. They pyrolyze it at a low temperature, and that turpentine comes out. So what do we use turpentine for? All kinds of things. It's been a solvent for a long time, a paint thinner, a polish. It's mixed in with wax. It's been used as a fuel in lamps, engines, and it's been used to flavor gin. In fact, for a long time, gin was made that way. So let's look at the one for engines for just a second. Just a little fun thing on the side. When Honda made his first engine, his own engine of his own design, he ran it on turpentine. Right? So when Henry Ford made his first engine, anybody know what he ran it on? Alcohol. Okay, when Rudolf Diesel made his first engine, what did he run it on? Vegetable oil, peanut oil in particular. Okay, all naturally derived substances. When Ferdinand Porsche made his first Porsche, what did he run it on? Electrons. The very first car Ferdinand Porsche ever designed was an electric car. So if you look at those four are like, you know, the leaders in the automotive world, and you look at what they thought they were creating, they all envisioned that they were creating an internal combustion engine that would run on a renewable fuel source produced by farmers in particular. Their concept was never that they were going to be run on fossil fuels. So, low temperature, we get turpentine. Turn up the heat a little bit here, and we start getting those oils coming out, cresol, creosote. Creosote's been more than just a bad thing going up our chimneys, though. It's been used as a drug for a long time, and in Japan is still marketed and sold as these drugs. And it's been used as a wood preservative and a meat preservative. In fact, you can buy bottles of creosote that you can put on meat. The EPA, if they had their way, would bar all of us from ever eating anything that looked like this, because they say that all the bad stuff in eating a piece of meat, you've all heard this about not eating charred meat, that the charring on the outside is the creosote that's in the meat or been applied to the meat. And so we turn it up a little bit higher, and we're still up here. We're just starting into this secondary phase of tar production. And we start getting this thick, gooey stuff come out, commonly called pitch. We used to be able to buy pitch in cans. We used to use pitch in place of tar to fix our roofs, things like that. It's used as a caulk, waterproofing. It's soaked into cotton and used as torches, hand torches. So those are the tars. Industry likes to have tars. The application I'm going to talk about here in a few minutes is application of wood gas in an internal combustion engine. Internal combustion engines do not like this. They do not want it going into them at all. So if you are processing wood at this temperature range and producing these kinds of tars, they will quickly destroy an internal combustion engine. In fact, to even begin to use them in an internal combustion engine, you have to take those tars out. So you have a gasifier, and it's going through a filtration system to remove those tars before it goes into the inlet of that engine. We're doing time-wise. Right. So the other thing that comes out is the solid. I broke it off. The char on the end of the stick. And people are using it as a soil amendment. Biochar is looked upon now as one of the best things you can add to the soil to improve its fertility. It also stores carbon. So if we back up to that chart I showed you, at the temperature range that I'm talking about here, how much char did we have left over? I think it was 20%. 20%. So if I put 100 pounds of wood into my gasifier, I'm going to get about 20 pounds of charcoal or biochar out of it. What can I do with it? Well, I could burn it. I could use it as a filter media. We have all kinds of filters that use charcoal. Or I can put it into the ground. In the ground, it does some very interesting things. So this is carbon, pure carbon. It's carbon that didn't go into the atmosphere. It's carbon left over from the wood, and we're going to put it back in the ground. When it goes into the ground, it does a few things. One of the things it does is it immediately locks up nitrogen that's in the ground. And I've read several studies that say that one of the ways that we can improve our factory farming is to put more biochar into the soil to lock up more of the excess nitrogen that's been applied and that is running off. It increases soil organic matter, aeration and water retention. You know, charcoal is basically like a sponge. It has lots and lots of surface area in a very small space. It locks up other compounds inside of itself. And the soil microbes like that. It's all right there where they can get to it. So biochar is a byproduct. You gasify at different temperatures. If that's your goal is to produce biochar, you're going to do it at a lower temperature. You can produce more of it, but you're also producing more of the other things, the tars and the gases, or the tars, excuse me. So, how do we gasify? Well, it can be as simple as take a can, put a bunch of wood in it, wood chips, sawdust, chunk of wood, put a lid on that can, make sure it's metal, and put it in a fire. It will bake that piece of wood and it will release the gas out of that piece of wood. And when you get done, you'll have a black chunk left over. Right now, my son is experimenting with packing a steel tube about that long, about that big around, with sawdust, has a steel lid on it, puts it in a wood fire, and you can see the flames come out the cracks of the lid. And they'll shoot out the side of the lid that far, leave it in there for an hour, maybe 2 hours, and the wood that was packed in, or the sawdust that was in there packed tight, will have reduced down to about 60%, and it'll be fine black charcoal. So that's the simplest way to do it. There are other ways of doing it. The problem with that is that when you pack that container full and you put it in the fire, it produces gas until the gas is gone from the wood that's in there. Then you have to recharge it. You have to take it out, dump it out, pack new sawdust in it, put it back in. That's called a batch process. We're doing a batch at a time, like baking a batch of cookies. So the batch process is where we load it with a quantity of wood. The output is variable because while we're unloading it and reloading it, no gas is being produced. We put it in the oven, gas production starts going up, levels off, and then we have to recharge it again so it drops down. That's called the batch process, used mostly for mobile applications. A stationary application has the advantage that you can use what's called the continuous process. You can feed these wood chips into the gasifier at a steady rate, just like fuel oil flowing out of your fuel oil tank into your fuel oil furnace at a steady rate. The one we're going to look at today is this one. I want to show you a few examples here. This is gasifiers being used for transportation purposes. And if you read Mother Earth News or any technical magazines, there's all kinds of articles now about putting gasifiers on vehicles. It was really prevalent, reached its highlight at the end of World War II because we severed most of Germany from having any fuel supply. And so people got very crafty, and I've read that as many as 50% of the war vehicles at the end of World War II were being run on wood gasifiers because they had no other fuel to use. So they put a tank on the back, a tub, packed it full of wood, put some wood under it, used that wood to heat the wood that's in the canister, ran a tube up to the front of the vehicle, sucked it into the intake manifold, and drove down the road. And so some modern versions of that is putting them in the back of pickup trucks. But you'll notice that by the time you load some wood in the back of that pickup truck, it's not much good for anything else. It takes a lot of space on a mobile vehicle to do wood gasification and drive down the road. They've even done it on motorcycles. I would not want to lean back on that motorcycle. This is kind of a modern version of this. It's all self-contained on a trailer with a tube running up that runs underneath the car up to the intake manifold. so you can drive around. I could possibly see it on a farm application where you're not driving on the road and you don't have to worry a lot about having trunk space and, you know, how convenient it is. And this is a garden tractor that has one on it. One of the reasons they could do it back here, it's kind of interesting, is that during World War II, most car engines were of what's called the flathead design, not overhead valves. The valves were in the block. And remember all those nasty tars I was telling you about? Well, they weren't doing much to filter those out. So they were sucking all these tars into the engines along with the gas. And after a while, the engines would quit turning because they were gummed up inside with this tar. Well, to service a flathead engine, you just take the bolts off the head, pull the head off. It's right there. All the valves are clearly accessible. The head's accessible. And I've read that they were pulling the heads off of these cars once a month and cleaning the tars out of them to keep them running. So think about that if you're thinking about doing an engine application. How many people have a EPA-rated wood furnace? Not one person. Okay. You may have read recently that the EPA, this is about 2 weeks ago, the EPA has had rated gasification wood furnaces on the market since 1988. And they are now trying to make it so that no manufacturer can manufacture a wood stove or a wood furnace that does not meet these qualifications. And they're getting a lot of pushback. I mean, a tremendous amount of pushback. This was just 2 weeks ago they announced this. So how does a EPA-rated wood stove work? Essentially, it's a batch process. You load a bunch of wood in here, you get it to burn, and you have these bottom part of it that's kind of on fire, and then you choke it off. You cut it off from any air, and you cut it off from being allowed to escape into the atmosphere. And what happens is all those gases that we were just talking about come off of that wood, and they accumulate inside that stove. And then at a preset time period, they turn on a fan that sucks those gases out of that chamber down across those glowing embers, and they introduce oxygen into it at the same time from outside, and they burn those gases, and that goes out the smokestack. An EPA-rated gasification wood stove is far more less polluting than a common wood stove, and it uses about a third the amount of wood to produce the same amount of heat. They also cost $1,000 to $2,000 more to buy new. But they like to see everybody that burns wood, excuse me, have that on their stoves. So in this case, we're just taking the gas and sucking it back down across the fire.
What is the heat exchanger?
Most of these have coils in the back part here, where the heat, as it's going out, heats the water that's inside those coils and circulate it back to the house that way. So this is a stationary continuous application. How can we make this thing run continuously for a long period of time? Okay. Well, one way is we have a big hopper, and in that hopper we fill it with wood chips. And those wood chips have to be a fairly uniform size. So somewhere between about a 1/2 inch square to about 2.5 inches square. That's so we can feed those wood chips into a gasifier with a screw, an auger. That's what this is right here. So you got a hopper full of wood chips. We bring those wood chips down into the auger. The auger brings it, in this case, to another auger. That goes into the gasifier. This gasifier, you may notice, is just burning those gases and creating steam, and taking that steam and running a generator off of it in all probability. That's another option instead of running it through an internal combustion engine. There's a company in Grand Rapids, excuse me, called Heat Transfer International. And they have a huge gasification project like this up by Howard City at a turkey farm. And what they're burning, instead of burning wood chips, they're burning turkey manure and taking the gas from it, injecting it with hot air, and using it to spin a turbine and generate electricity. So just like with your wood stove at home, these wood chips should be very low in moisture. You should not be burning wood that is over 20% moisture in any wood stove under any circumstances. That is what's considered to be seasoned firewood. At least 6 months, preferably a year, drying from the time it was cut from a live tree. How many people do that? Good, good. All right, so I'm going to describe to you how I'm going to apply this at my farm, what my goals are, what the system looks like, and you're all welcome to come over and help build it or look at it. So I live about 3 miles from here on the corner of Piper Road and Cedar Creek Road. I have a 43-acre farm, and I have another farm that has about 80 acres, and I'm raising grass-fed beef. That's been my retirement plan. I was in my bank the other day and it said, "Do you have a retirement plan?" when you walked up to the window. And I said, "Yeah, I got one." They said, "What?" I said, "I'm raising cows." And they kind of went, well, that's what I'm doing. And I would like to have this farm be as profitable and as self-sufficient and as energy producing and as recycling as I can make it. So I want to produce clean renewable energy through wood gasification. I want to use this wood gasification to produce enough heat excuse me, for the building it's contained in, which I'm calling the Energy Center Greenhouse. We'll look at that in a second. My home and my shop for 6 months out of the year. I don't want to run this process in the summertime. So I'm going to produce all the electricity for those buildings. I want to produce some biochar to recycle back onto my fields and improve the fertility in my hay fields. There are some outputs from the gasification process that need to be recycled back into useful products. There's a little bit of a challenge with that. We'll talk about that in a second. I want to grow human food year-round. So the building that it's contained in is partially a greenhouse, and the heat from this process is going to keep that greenhouse a greenhouse all winter long. So I can grow food all winter long for my own consumption and possibly for sale. Any of you went to my son's presentation this morning, that's where his aquaponics program is going to be located. I want to grow cattle feed. Anybody went to the biodigester presentation? They talked about growing cattle feed, fresh cattle feed in the wintertime in greenhouses. I'm doing that, or plan to do that, growing barley sprouts. And in the summertime, when this thing isn't providing electricity, it's a standby generator for my entire operation. And we've had quite a few power outages of late. So this is my farm. This is the corner of Piper Road and Cedar Creek Road. 43 acres. This is Fair Lake out here, this kind of dark spot here. Fair Lake has the distinction of having the southernmost pair of nesting loons in Michigan. There's an aerial photograph of my farm. The reason I wanted to show you this is that this is my house, this is my shop. Looks a little different now, but basically the same size. And there was originally a barn right here, and this is straight south. So this barn is about halfway between my house and my shop, the foundation of that barn, and it's in a south-facing hill. Looking at that above, my house, my shop, this is the original barn foundation. This is the building I'm proposing to build around that existing foundation. That's what the foundation looks like. Still pretty structurally solid. There's a concrete floor under that. And the building that's going to go there is going to look like that. Like a horse barn, kind of. That building is 36 feet wide this way, and it'll be 72 feet long in the other plane. And half of it's going to house a greenhouse that's going to house an aquaponics program. So there's fish tanks that'll be located on the back wall, grow beds up on the front where the windows are. The water is circulated from the fish tanks through the aquaponics grow beds and back. That water will be heated by this process. The building itself will be heated by the waste heat from the engine of this process. And go a little faster. So this is looking at it from the south. That building will sit right here in this hill. So it'll be earth sheltered. That's an overhead view of what's going inside this building. I'm going to skip through here. So this is the gasification process. So I'm putting a silo right next to this building here that's going to contain wood chips. I have a tractor with a chipper shredder on it. The wood we harvest off the property will be fed into that chipper. We get this wood from, we have a sawmill, so we end up with quarter rounds around the outside of the logs, limbs off of trees, small branches, or what's called coppicing. Anybody know that word? What is it?
You chop the tree down, let the saplings grow up,
Okay.
and then harvest those along the time, and when they get bigger or whatever.
Okay. It's chopping a tree down, but it's also intentionally growing trees that grow very fast. And when they get to the point they're 5-6 feet high and they're about yay big around, you cut them off and you use that wood for firewood. And you can grow firewood, your own firewood, much faster and much more efficiently than cutting down big trees. So we're in the process of planting trees for coppicing. So, okay. So all that wood gets fed into the chipper shredder, which blows it into the silo. The silo moves it out into a hopper that's inside the building. And I have pictures of all this in a second. That's all done with augers, moving these wood chips. The wood chips come up here as a gasifier, which is a heat chamber that's around that auger. The auger's inside a tube, and there's a heat chamber around that. There's an engine and a generator here that's producing the heat and the electricity. We're going to collect the biochar coming off of this in barrels. We're going to clean that gas going through a centrifuge. Centrifuge just takes that gas and spins it around the inside of a container. The heavy particles fling out against the walls of the container and fall down. The finer particles have to be filtered out through some kind of filter media. That can be wood chips, it can be charcoal, it can be cloth. So we're going to try and recycle all of the fine particulates we get out of this through the filtering system. This is a heat exchanger. The water going through that aquaponics system, and the water going to my house, and the water going to my shop are all going to meet here and be heated by this process. And I have a wood furnace for backup, and this doesn't work like I thought it was going to. This is a side view. Yeah.
Where in the process do you bring the moisture content down to 20%?
2 places. One, I don't cut, well, if I'm cutting wood that I'm coppicing, it has moisture in it. Most of the time I'm cutting wood that is already dead in the woods. It's been dead for a year or two, so it's already got a very low moisture content. It's also being put into this wood chip silo at a very early time of the year, so it dries inside the silo. The silo is vented. I've actually even thought of pumping heat through the silo to help dry the wood. Okay? So this is a side view. This is my son, not me. Pushing a piece of wood into a wood chipper. The chipper chips it and blows it into the silo. The silo fills up. This silo, I'll get into that in a minute. maybe. This auger brings it in here, drops it in this hopper. The hopper is a grain wagon, common farm piece of equipment. Another auger takes it out of that hopper. The gasifier right here is being heated by the exhaust from the engine. So remember the temperature range we were talking about? 600 to 800 degrees centigrade? That is exactly the amount of heat that comes out of your exhaust out of an internal combustion engine. So once you get this engine going and running, it'll run on the gas that's being produced, and it'll provide the heat to make the gas. It's a self-perpetuating process.
Does that take all the heat?
What's that?
Does that take all the heat? Is all the heat transferred into the gasifier, or is there still heat that you can put that back through your silo and dry it out?
Hang on, we're getting there.
Sorry.
We're getting there. So the wood goes through here, it's in a screw, remember, inside this tube. It gets heated, it's turned into charcoal basically here. Comes up here, falls through a hole in the bottom of the tube into a barrel, and it's collected as biochar. Put in a manure spreader and spread on the fields, if that's what you want to do with it. Okay, so the gas. There's a centrifuge right there. So the gas that's collected off of this goes into a centrifuge, then it goes into a filter, and then it goes into a heat exchanger. Okay, so that's the gas coming off of the gasifier. The exhaust gas also goes into that heat exchanger. So after I run the exhaust from that engine through that gasifier chamber, it's then going to go into that heat exchanger. I'm going to remove the rest of the heat I can get out of it there before it goes out into the atmosphere. Oh, over here. So let's look at this as pictures. Okay, sawmill, cutting quarter rounds off of it, runs into a standard chipper anybody can buy. Instead of just piling the chips on the ground, blowing them into a silo. Inside the silo is an auger. Wood chips are falling down into the auger. The auger's augering it into the hopper that's inside the building, which is a grain wagon. You can buy these dirt cheap. They're sitting all over the countryside. They most of them have an auger on them. That's what this is. I couldn't get a good picture of a gasifier. This is the screw inside there. Around there is a chamber that the exhaust is being pumped through that's heating that chamber. The gas comes out, goes through a centrifuge, goes through a filter, comes into a tank that is the heat exchanger. So the gas will be going through the copper tube. The tank is full of water. It's heating the water. That's where I'm exchanging hot water to my house, to my shop, to the aquaponics grow beds. You look puzzled, Larry.
No.
Oh. And then it goes from there to this. This is the generator that I bought. Came out of a AT&T service truck. It has 200 hours on it. These units are rated for about 15,000 hours before they need rebuilt. So you can figure out how long you can run it. A couple of years at least before you have to do any service, or not any service, but any major overhaul to it. This is a 1 liter unit, 67 cubic inches. It puts out 69,988 BTUs an hour, and it runs a 10 kilowatt generator. So let's play with those numbers a little bit and see if I can do what I think I'm going to do at this farm with this unit. So, in an average internal combustion engine, where does all the energy go? You go down and you buy, let's throw some numbers here. Let's say you pay $3 a gallon for fuel. And you put $3 of fuel in your car. How much of that energy that you just put in there is actually causing movement of your car down the road? About 30%. Actually, you're doing really good if it's 30%. It's between 25 and 30%. Where's all the rest of that energy gone? All went out the water jacket of that engine, and also went out the exhaust pipe of that engine, out your radiator and out your exhaust. So when you're driving down the road and you put that $3 of fuel in your car, you're throwing $2 of it out the window, and $1 of it's making that car move down the road. So we'd like to capture some more of that. It's hard to capture it in a car, though. But when you got a stationary engine, you can capture that heat pretty easily. I can pump, remember, I'm pumping this heat from the exhaust and the heat from the gasifier into my heat exchanger. So let's play with some numbers on this. How much heat is produced? So my engine unit produces roughly 70,000 BTUs an hour. We're throwing 2/3 of it away in a car. So let's multiply that by 2/3 roughly. So now at about 49,000 BTUs an hour worth of waste heat. If I can capture even 50% of it, that means I'm capturing roughly 25,000 BTUs an hour. Most of these systems in Europe are capturing 70 to 80%. I'm being very conservative here. If I can capture 50% of it, that's how many BTUs an hour I can get. The average home in Michigan requires 11,520 BTUs an hour to heat. Okay. My home, I guarantee, takes far less than that. Same with my shop, and the same with the building that this is housed in. So I think I got enough heat to do all the things I want to do. How about electricity? Anybody know how much electricity your house is using? Too much. Will a 10 kilowatt generator run your house? Yeah. You better, if it won't, you better be moving. Yeah, 4 to 5 kilowatt generator will run most homes, and that's most homes that are fairly energy intensive. So I think I got enough electrical capacity to run my home and this shop and the building too. There's some ways you can improve this efficiency. Turns out that wood gas likes to have a compression ratio that's right in between a gas engine and a diesel engine to get the maximum power back out of that wood gas. So one of my phase 2 operations is I used to build race engines. So I used to build a lot of engines that had this compression ratio. So I think I can take my little generator and hot rod it and make it produce more power out of the same gas. This is a flow chart of the whole process here. I'm not going to spend a moment on this. I want to show you some other things here. But this is just how it flows around here. We're going to look for a minute. One thing I haven't talked about is what comes out here. I'm recovering everything else here. I can use the tars as a fuel. I can use them as a preservative. I can use the biochar in the ground. I can use it as a filter media. I can burn it. But what's coming out of the exhaust pipe ultimately back into the environment? Oh, let's skip this one, but I went through a calculation. If I ran this generator continuously for 6 months at maximum output, 10 kilowatts, it would take 9.6 cords of wood. The average home in Michigan right now to heat is 7 to 8 cords of wood, just to provide heat. Huh? Full cords. Full cords. So what's coming out the exhaust pipe? Not too much. One of the worst things that's coming out is nitrogen oxide. That's what all the car manufacturers are so concerned about. That's why we have catalytic converters and all this stuff. Turns out that I could, one, go down to the local junkyard and buy a catalytic converter off a small car and put it on there and I'd be fine. But let's kind of put this in perspective. Where does nitrogen oxide into the atmosphere come from? Most of it comes from the nitrogen we apply to farmland. The vast majority of it. Very little of it comes from agriculture or from internal combustion engines are burning biomass. I don't think I'm too far off polluting the planet there. CO2. If you run an engine on natural gas, which we've heard a lot about today, an engine running on wood gas performs very similarly. Power-wise, pollution-wise, everything. It's very similar to running it on natural gas. So we're using wood gas here. Remember, natural gas pollutes 50% less than coal. So I'm comparing it to that. Plus, I'm capturing 20% of that carbon and putting it back into the soil. Plus, burning wood is considered to be a carbon neutral activity anyway. So am I really contributing to the carbon pollution? I say no. That's controversial, but the general consensus is it does not add to the carbon cycle. The last one is those bad guys I was telling you about at the very beginning. Polycyclic aromatic hydrocarbons. They're the worst. But we're going to gasify at a temperature below where they're created. So that's good. That's one good thing. And the other is that where do the bad guys come from most of the time anyway? It comes from coal, burning coal. And right now, the EPA is going to ban coal-based driveway sealers. That'll happen this summer. Because the vast majority of PAHs that are being released into the atmosphere are being released off of pavement that's being recoated with coal tar and not asphalt. So there's some places, now some states have already banned it, and most places will sell you a driveway sealer that is not coal tar based. So that's coming down the road too. So I'm 1 minute ahead of time. Mike.
Brian, I know we talked briefly about this, but I'm real interested in your continuous hopper-fed gasification process. I see you're looking at running your generator and different things. What about a storage medium like a bladder or some way? Do you have any ideas for storing excess to use at a different time, or what type of challenges you'd have in a storage medium?
Yeah, that's an interesting question. It turns out to store it, you either have to have a gigantic container, which is not safe to have a gigantic container full of this explosive gas, or you're going to take it and compress it, which is also not a very safe activity to home compress gas. The other trick to this, remember the auger that's feeding the wood chips through the gasifier? The engine requires a certain amount of gas to run at a certain RPM. So this electric motor that's turning this auger has a variable speed on it. And that speed is what's controlling how much gas is being produced. And you want to produce just as much gas as what the engine is demanding. Well, you can produce more, but the pollution level, in particular the nitrogen oxides, start going way up if you feed more gas than what the engine is demanding. So I'm going to try and coordinate those two with the variable speed of the auger. Yeah?
You've got the temperature to gasify your wood chips. Do you have the heat capacity from the exhaust to get them fully charred?
Say that again?
So you've got the temperature, you've got a high enough temperature.
I got high enough temperature, right?
But there's the idea of heat capacity as well, right?
Right, there's a certain amount of heat that has to come out.
Yeah, have you calculated that?
I haven't calculated. All the calculations I've done for this are based on, again, Europeans who have done this for a long time, who have run small engines like this continuously on gasifiers.
And then do you end up just not fully charring the wood, or does it really?
No, again, going back to the variable speed, I'm just going to slow down how fast, or speed up how fast those wood chips are going through that gasifier to produce X quantity of gas to feed into that engine. But it'll always be charred, and it's just how much of it, how quickly you do. Yeah.
Are there commercial systems?
Not that I'm aware of. Again, probably in Europe there are,
Oh,
but I have never seen one here.
We have one at the City of Battle Creek City Hall and Police Department. That's how those two buildings are heated.
Really?
It's a biomass boiler there.
A biomass boiler? Okay. And what are they using for the biomass?
Wood chips.
Wood chips. Oh, cool. I'd like to see it. Yeah. Steve?
What species of trees do you use are you growing for coppice?
Well, there's a variety of them that you can grow. It depends on how fast you want them to grow. Josh, some people actually burn willows because they grow so fast, but the heat value of willow is very, very low. That's one, and we're also looking at black locusts, because we're looking at growing black locusts to make to replace pressure-treated wood. Yeah, so we're going to coppice some of that and grow some of it, and it's Black locust is the densest hardwood you can buy. Yep.
Well, I'm just curious, I know that there's been a movement towards using wood for heat a lot lately.
Mm-hmm.
You kind of feel more independent because you can go out and harvest dead trees from woodlots and things like that. But when you're doing something like this and you're relying on it so steadily, don't you think that you would, I mean, I guess with the coppicing you can supplement that, but at some point you would run out of dead stuff in woodlots, and I don't know, like it's not being replenished kind of thing.
That
Because
could,
it takes a long time for trees to get up to be as large as you would. I mean, you can find decently sized trees, and I'm sure you'd get a lot of wood chips from something like that.
it's true. And then a lot of people have that concern. If you look at Michigan as a whole, so Michigan 100 years ago was just about completely denuded of trees. You wouldn't recognize what we see out here now.
Right.
And so what we see out here now is second growth forest in Michigan. And it's been estimated that we are reclaiming less than a third of the deadfall that falls in Michigan forest now. So there's a large supply of wood without actually going out and harvesting whole forests that's available, for one. For two, you do have to have a wood supply. I mean, I'm looking at that myself.
Right.
You know, if I were to run this thing continuously for 6 months, it's going to take 10 cords of wood. And I used to heat with wood 100% of the time. 10 cords is a lot of damn wood to process. It's a lot easier to process when it's this big around,
Right.
and you cut it off and you feed it into a chipper than to saw it up with a chainsaw, split it, stack it, move it. It's much, much easier. So you go out into a forest and you take the branches and the deadfall and don't even worry about the big stuff. I have on my farm roughly 7 acres of woodlot. It produces more wood than I could possibly harvest in a year, way more. So.
Sorry.
In the interest of keeping our time, since this was supposed to end 5 minutes ago, we do have sessions following at 2:10, so this is
Oh,
the break.
2:10?
Yeah, I think that's what the schedule says.
So Brian's gonna run your chipper and
And Brian might stick around for questions
Yeah, I'll
in the meantime, but
what's that?
before you leave, let's give Brian a great hand.